In this video, we'll be finding every possible rational root of a polynomial function. So let's dive in and look at this first example. So I know with what we've learned so far, you're going to want to try to use factoring here. So let's try and see what happens if we do. Now, because we have four terms that have no like terms with them, we would have to use factoring by grouping here. So here we would group it into pairs and we'd factor out an x squared, which would give me x minus 8. And then I know that I need to factor something out of here to get it to match this parenthesis part. And when I look at 11x plus 20, there is absolutely nothing I can factor out of there that would result in x minus 8. So the problem here is that we absolutely cannot use factoring here to solve this. So we're going to have to do something different. So what we're going to have to do is we're going to have to use the rational root theorem to help us. So the rational root theorem at least allows us to find, a list of possible roots that could be roots for or solutions for this particular function. And so we're going to divide all of the factors of 20, which are 1, 2, 4, 5, 10, and 20. We're going to divide those by the factors of 1, which luckily are just 1. So our list should be fairly small. So we're going to do 1 divided by 1, which is 1, 2 divided by 1, which is 2, 4 divided by 1, which is 4, 5 divided by 1, which is 5, 10 divided by 1, which is just 10, and 20 divided by 1, which is just 20. So our possible roots are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, and plus or minus 10, and then finally plus or minus 20. So these are all of our possible rational roots that we need to test in order to find all of the real solutions of this particular polynomial. So we are going to dive in and start testing these using synthetic division, because we know that if we can find a root using synthetic division, that it will have a remainder of 0. And these are the numbers that we need to test in synthetic division if we want to try to find one of the real solutions. So I'm just going to start with the ones here. I'm going to start with positive 1, and I'm just going to see what happens if I use synthetic division. So I'm going to pull the 1 down, multiply it by 1, then add straight down, multiply it by 1, multiply it by 1, and we find that we have a remainder of 24. So what that tells me is that 1 is not a real root of this function. So then I'm going to move on and I'm going to test negative 1. So we're going to do 1, negative 8, 11, and 20, and we're always looking for a remainder of 0. So we pull the 1 down, multiply it by negative 1, add straight down, multiply it by negative 1, add straight down, multiply it by negative 1, and look, we get a remainder of 0. So what that tells me is that negative 1 is a solution, or it is a root or x-intercept, all those words are interchangeable, of this particular polynomial. And what it also tells me is that if I were to put that into the equation in factored form, it would be, remember, we would pull it out to check if it's a factor, so it would be x plus 1 in the equation if we were to rewrite this. So what's kind of cool is we can rewrite this polynomial, f of x, is equal to, instead of writing this, we can start to write it in factored form using what we now know is a factor. So we can do x plus 1, and we know that when we took this function and divided it by x plus 1, it gave us this as the other polynomial that would be there. And so this is the constant, the x, and the x squared. So what's really cool is we know that x plus 1 times 1x squared minus 9x plus 20, we know that that multiplication problem equals this. So essentially, by using synthetic division and the rational root theorem together, we were able to work backwards and we were able to write this into a slightly more factored form. Now, from here, our goal is to rewrite this part even further, and there are two ways that we can try to approach that. So, one way is that we can try to approach it with factoring. So I'm going to do that over here. The other way is that if you forget how to factor, you can use, because this is a quadratic with a squared, you can also use the quadratic formula if you would like. So we're going to solve this in two different ways, using both factoring and the quadratic formula to show you why in this instance it worked. But I want to show you how if factoring for some reason doesn't work, the quadratic formula gives you another option. So our goal here is to find all of the solutions or all of the roots. So we're going to set f of x equal to 0 because that's ultimately what we're trying to solve here. And for this first part, we're actually going to use factoring because this one actually does factor really nicely. So if I take a look here at x squared minus 9x plus 20, I see I have an a value equal to 1, a b value equal to 9, and a c value that's equal to 20. So if I were to factor, and the b value should be a negative 9, sorry about that. If we were to factor this, we need two numbers that multiply to a times c, which is 20, and add to negative 9. Well, two numbers that do that are negative 4 and negative 5. And because our a value is 1 here, we can use this as kind of a shortcut and write x plus 1 and x minus 5, x minus 4. So we were able to use our knowledge of factoring trinomials, synthetic division, and the rational root theorem to get this equation to here into fully factored form, and then we set it equal to 0 to find all of our roots, and we can use the zero product property here. And we know that our x values that result in solutions or roots or x-intercepts, all of those words are talking about the same thing. We're going to get x equals negative 1, positive 5, and positive 4. So this one will allow us to use factoring. However, we're going to encounter instances where factoring doesn't work. So I want to show you how the quadratic formula is going to be a good option here if you can get a quadratic that has a power of 2. So here we're going to do the same thing. We're going to do 0 equals x plus 1, and then we're going to do x squared minus 9x plus 20. So this first one here, we can find that x is just equal to negative 1. That's an option. Now, I can use the quadratic formula on this part to get my other two solutions if for some reason I don't do well with factoring. So again, we start with a equals 1, b equals negative 9, and c equals 20. So remember our quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2 times a. So negative b would be opposite of b, so that would be a positive 9, plus or minus the square root of this turns into 9 squared minus 4 times 1 times 20. Well, that is all then over 2 times a, which is 1. So this turns into 9 plus or minus 9 squared is 81 minus 4 times 1, which is 4 times 20, which is 80. And you could use a calculator to calculate that part under the root. I'm just doing it in my head as we go. Then we divide that all by 2. We need a little more space here, so we'll move it up. So this would be 9 plus or minus the square root of 1 over 2, which the square root of 1 is just 1. So it's 9 plus or minus 1 over 2, which would be 9 plus 1 over 2, and 9 minus 1 over 2, which 9 plus 1 is 10, divided by 2 is 5. 9 minus 1 is 8, divided by 2 is 4. So we get those same values of negative 1, 5, and 4. Now this one is nice because we could just factor it. But again, that's not always going to be the case. It's going to depend on the problem and if it is factorable. But our goal with all of these problems is to find the solutions when f of x, or our y value, is equal to 0. And we can use synthetic division, rational root theorem, factoring, quadratic formula, all of those things to help us. So let's take a look at this second example here. I know that we would like to try to just factor this using our factoring strategies. unfortunately, if we try to do so, what you are going to discover is that the only factoring strategy that we can use on something that has that cubed, squared, and an x value and a constant is the factoring by grouping strategy. And if we try to do that, so here we would only be able to factor out an x squared. So we would get 2x plus 5. And then here we'd need to get the parenthesis part to match. And honestly, from looking at it, there's nothing we could factor out of this in order to make it match 2x plus 5. And because of that, we cannot use our normal factoring strategies here. We're kind of out of luck, and we have to use something else. So this is really where the rational root theorem comes in. So we have our rational root theorem that will at least give us an idea of a place to start. It gives us an idea of what our possible zeros for this function are. So I'm going to take all of the factors of 4, which are 1, 2, and 4, and I'm going to divide them by the factors of 2, which are 1 and 2. So I'm just going to start by taking factors of 4. So I have 1 over 1, which is just 1, 1 over 2, which is just 1/2. Then I have 2 over 1, which is just 2, 2 over 2, which is equal to 1, so that's a repeated 1. And then I have 4 over 1, which is 4, and 4 over 2, which is 2, and that is also a repeated 1. So my rational roots include plus or minus 1, plus or minus 1/2, plus or minus 2, and plus or minus 4, which is kind of nice here because at least it's only a list of 8 possible roots that we need to test. So I'm just going to start picking roots to test and test them. So let's start with a different number this time. Maybe let's start with the 2's. So I'm going to start with positive 2 and see what happens with my synthetic division. So I have 2, 5, negative 11, and 4. So I pull down the 2, multiply it by 2 to get 4, add down, multiply it by 2, add down, so now we have 7, multiply it by 2, and here I get a remainder of 18. So positive 2 is not a root. So now let's try negative 2 and see what happens. So here we have 2, 5, negative 11, and 4. So we pull down the 2, multiply it by negative 2 this time, which is negative 4, add down, multiply it by negative 2, which is negative 13, multiply it by negative 2, add down, which is then 30, because I have a remainder of 30. I know negative 2 is not a root. So now let's go try the 4's. So we've exhausted the 2's, let's try the 4's. So we have 2, 5, negative 11, and 4. So we pull the 2 down, 4 times 2 is 8, add down, 4 times 13 is 52, add down, 4 times 41 would be 164, so that's got a massive remainder, so that one doesn't work. So now let's try negative 4. So now we have 2, 5, negative 11, and 4. So negative 4, we bring down the 2, we multiply it by 2, which is negative 8, add down, that's negative 3, multiply it by negative 4, that's a positive 12, add down, multiply it by negative 4, whew, and finally we found one with a remainder of 0. So I know that negative 4 is a root for my function, and I know that if I were to put this into the equation as a factor, it would be listed as the opposite here of negative 4, which is going to become x plus 4. So I can take my function here, which is f of x, and I can set it equal to x plus 4, and then I can use this part here to figure out the second piece. Remember, this is my constant, this is my x value, and this is my x squared. So from here, I can write this into my function as 2x squared minus 3x plus 1. So there I have something that is slightly more factored and will hopefully help me to find all of my real roots for this function. So now what we need to do is we need to brainstorm what else we want to do in order to actually find more values that make this function true. So here, we now need to focus on this piece here because this I know is already a factor and fully done. So the next thing I want to do is I want to look at and decide, okay, is this particular function factorable? Well, I see I have an a value of 2, a b value of -3, and a c value of 1. So if this is factorable, I would need two numbers that multiply to 2 times 1, which is 2, and add to -3. So two numbers that multiply to 2 and add to -3. If I think about that, I can get -2 and -1. So I would be able to factor that, and we could use our factoring trinomial strategy to factor this further. So here we could take 2x squared minus 2x minus 1x plus 1, factor out our greatest common factor here, which is 2x, so we get x minus 1. Here we could factor out a -1, which would then allow us to get that x minus 1 matching, and then we would have 2x minus 1 times x minus 1, and then from here we can plug that all back into our equation. So let's see if we can move this. There we go. And we would now have a final factored form of f of x is equal to x plus 4 times 2x minus 1 times x minus 1. So now what I can do is I can find all of my possible roots or all my possible solutions by setting this equal to 0. So now I just need to solve this to find all of the possible roots. So I set each little part equal to 0. So if x plus 4 equals 0, this would be a solution of x minus 4. For this one, we would add 1 to the other side and then divide by 2. So I would have x equals 1/2. And then for this one, it would be x is equal to 1. So there's our list of all of our possible roots, all of our possible solutions for this particular function.